The last topic in section 1.2 is points of intersection. Points of intersection are ordered pairs that are solutions to two different equations. Graphically, the points of intersection are where the curves intersect, where they go through the same point. Algebraically, to find those points, what you'll do is you'll set the y values equal to each other and solve for x. So in example 1, let's find where the two curves intersect. Y equals 4 minus x squared and y equals 4x minus 1. So what we'll do here is just set y equal to y. Well, if on the first curve you've got y equals this expression, and on the second curve y equals that expression, we just want to equate these and get rid of the y's basically. So we'll get 4 minus x squared equals 4x minus 1. We want to solve this for x. Whenever you have an equation with two different powers of x involved, you always want to factor after getting 0 on one side of the equation. So we want to get equal to 0 and then factor. Whichever way you want to do this is okay. I don't like having a number in front of the x squared that's negative. So to avoid that, I'm going to bring the x squared over to the other side. I'm also going to bring the 4 over to the other side. So we'll have minus 4 plus x squared. Minus 4 plus x squared. What we have on the left side will be 0. Then we'll have x squared plus 4x. Negative 1 minus 4 is minus 5. Now we want to try to factor the right-hand side here. We've got a 1 in front of the x squared, so we're going to try to reverse FOIL this. Two numbers that multiply to negative 5 and add up to positive 4 will be plus 5 and minus 1. Setting each of these factors equal to 0 gives us x equals negative 5 and x equals positive 1. Now, if we wanted to find the coordinates of the intersection points, what we would do is take each of these x values and plug them in to either one of these equations. You will have to get the same thing no matter which equation that you plug the x values into. Otherwise, you wouldn't have found a point of intersection. So I'm just going to use the easier one. I guess each one is easy in its own way, so I don't know, I like the first one. So I'm going to plug a negative 5 into the first one. Be careful here when you are squaring a negative number, you need parentheses around that. Negative 5 squared is 25, and if we have 4 minus 25, that gives us negative 21. So our coordinate, if we were asked to put it in a coordinate, would be negative 5 comma negative 21. That would be one of our intersection points. For the other intersection point, if we plugged in a 1, 1 squared is 1, 4 minus 1 is 3. And so the other point of intersection would be 1 comma 3. Now I would suggest that you graphed both of these, both of our original equations, in your calculator, or there are many websites you can go to graph these things if you don't have a graphing calculator, and find where they intersect to just check your work. Although that is a way that you can find intersection points, you should also know how to do this algebraically. In example 2, we have y equals x to the third minus 3x squared plus x minus 5, and y equals negative 2x squared plus 13x minus 5. None of these look significantly more complicated, but the same thing is going to happen. We'd like to just equate these and then try to solve for x. So the first thing we should do is just write down x to the third minus 3x squared plus x minus 5 is equal to negative 2x squared plus 13x minus 5. Now we want to get this equal to 0 on one side so that we can then factor. Again, I like to have the leading term, the highest degree thing, have a positive number in the front. So I'm going to leave this x to the third on the left, and I'm going to bring all of this stuff over to this side this time. So in order to do that, we will add 2x squared. I'm just going to put that underneath the appropriate power, minus 13x, and then plus 5. That's going to cancel out everything on the right-hand side. On the left-hand side, we'll have x to the third. We've got negative 3x squared plus 2x squared, so that's minus 1x squared. We've got positive 1x minus 13x, so that's minus 12x. And then the negative 5 and the plus 5 cancel out. So it looks like here is what we have on the left side. Now we want to factor this. There is a GCF that you can take out of an x. When we do that, we'll have x times x squared minus x minus 12. Let's continue factoring further because we've got a nice quadratic here that's got a 1 in the front of it that we can probably try to reverse FOIL. Two numbers that multiply to negative 12 and add up to negative 1 are minus 4 and positive 3. Now here we have three things multiplied. We got to set each of these equal to 0. Don't forget about this x here. That counts as a factor. So when you set that equal to 0, we will get x equals 0. When we set x minus 4 equal to 0, we get x equals 4. And when we get set x plus 3 equal to 0, we get x equals negative 3. And here are all of our solutions. Again, we could go ahead and find the y coordinates of the intersection points, but we found the x values and that's generally good enough. In the context of economics, the point of intersection of the cost and revenue graphs represents what is called the break-even point. In this course, we will look at a lot of economics applications. The breaking even point is one special thing that we need to know what that means. Again, it is the intersection of the cost and revenue graphs. Another way to think about this is your profit equals 0. For example, you are setting up a part-time business with an initial investment of $15,000. The unit cost of the product is $11.80, and the selling price is $19.30. Let's find the break-even point. So in other words, this is how many items that you need to sell in order to not make any money, but also not lose any money. So that's what our breaking even point means. So we need to find our revenue and we need to find our cost, and then we will set them equal to each other. So remember that revenue is equal to price times x, or x times price. Either way is fine. And price is the price for one item, the price that you are selling one thing for. So here, the unit price is $19.30. So when we write our revenue equation, we can write it as x times $19.30. And this is just 19.3 times x. Our cost equation can be thought of as our fixed cost, if there are any, plus our variable costs times x. And remember that x is always the number of things made or sold. So in this case, we have an initial investment of $15,000. This does not depend on the number of items that we produce. So this is our fixed cost. It costs us $11.80 to create each product. So this is what we will call our variable cost. So to build our cost equation, this will be 15,000 plus 11.8 or 11.80 multiplied by x. Now if we want to find the break-even point, what we'll do is set our revenue, which was 19.3x, equal to cost, which was 15,000 plus 11.8x. I want to solve this for x. So in this case, we do have x in more than one spot, but it's the same power. So we can just kind of isolate the x. So we'll subtract 11.8x from both sides. If you combine those terms together, 19.3 minus 11.8x, that gives us 7.5x. We've still got 15,000 on the right-hand side. So lastly, we'll just divide 15,000 by 7.5. That comes out to be 2,000. So we need to sell 2,000 items to break even. So if you were to graph each of these equations, the revenue and the cost equation, we would have x on the horizontal axis. And our revenue equation is 19.3 times x. And we'll review linear equations in the next section, but you should have a sense of what that looks like. The 19.3x tells us that we've got a y-intercept of 0 and a slope of 19.3. So this just looks something like this. I don't need to get into the specifics right now, but this is the revenue equation. Now, I'm not drawing it past x being negative because it doesn't make sense for us to sell negative items. So here's just the, for a positive x, this is the graph of the revenue. Now, our cost equation, again, we will review linear equations, but this is the y-intercept and this is the slope. So the cost equation, if we sell 0 items, we still have to pay $15,000. So the cost is going to look like this. Maybe here is the 15,000. It doesn't rise as steeply as the revenue does, so it might look something like this. So here's cost 15,000 plus 11.8 times x. Now what we found is the place where they intersect, right here. Now the break-even point is where they intersect, right here. So we found that the x value where they intersect is at 2,000. You can see that at the intersection point, one of them, they cross, whichever one is on top and which one is on the bottom. In the first part here, before 2000, the cost is above the revenue. So we could write that as an inequality. We could say that the cost is greater than the revenue. So we're losing money. On the other hand, after the intersection point, they flip-flop. The revenue becomes larger than the cost. And that keeps on happening if we were to extend our graph. So here, the revenue is above the cost. And so here we are making money or making a profit.